And we move on to the last talk. Thank you. To the last talk of the session. So Matteo will talk about optimization-aware compiler-level event profiling. It's from USI, Università della Svizzera Italiana. And the stage is yours.
Okay, just a second. Okay, so thank you for the introduction. This is a joint work done in collaboration with Aleksandar Prokopec from Oracle Labs, Andrea Rosà, and Walter Binder from Università della Svizzera Italiana, Switzerland. This is a top-class journal first article. It's actually 45 pages long. So in this presentation, due to a matter of time, I summarize only the main points of our work, providing a high-level overview. For in-depth explanation of the challenges, profiling accuracy, and implementation details, please refer to our article. So to analyze the effect of compiler optimizations, compiler developers usually employ either hardware performance counter or source-level, bytecode level, and machine code level instrumentation. While the latter approach provides more useful information, it is well known that source and bytecode level instrumentation leads to inaccurate measurements. This is because of compiler optimization's effective event counts. Machine code instrumentation instead is too low level. It does not allow collecting bytecode level metrics. Moreover, neither of these approaches allow collecting information about compiler-generated events, such as speculative type checks and save points. Compiler level instrumentation may solve these issues. However, also this kind of instrumentation needs to be carefully designed to be accurate, especially when profiling many different event types at the same time. I would like to present here the contributions of our work. In our work, we propose a novel instrumentation technique to efficiently and accurately profile the execution of compiler-generated events. We propose two path profiling strategies to count 43 different event types at the same time. And we implement our two strategies in the Graal JIT compiler for the Java virtual machine. Moreover, we propose a modification to the standard path profiling algorithm that makes it practically usable in modern JIT compilers. Then, we use our technique to identify the reasons behind the performance improvement and the causes of unexpected performance degradation. Finally, we evaluate our two strategies using the Renaissance and Takapo benchmark suites. Experimental results show significantly lower execution time overhead with respect to naive implementation. Before explaining our technique, I would like to present a background, starting from the terminology. In this presentation, we'll focus on just-in-time JIT compilers. Just-in-time compilers take as input a portion of code called the compilation unit. At the beginning of the compilation unit is transformed into the most suitable representation that we call intermediate representation, IR. Compilers usually perform manipulations in successive compiler phases that we call phases for short. Successive phases form the compilation pipeline. Within the compilation pipeline, the IR abstraction does not remain the same, but progressively gets closer to the machine code. We call this process of transforming the IR by removing abstraction lowering, and the phases that perform lowering phases. For example, at the beginning of the compilation pipeline, we may find load field instructions that specify a load of an object field. Closer to the end of the compilation pipeline, load fields may be lowered to read instructions that specify a read of a memory address instead. We implement our technique in the Graal compiler. Graal is a state-of-the-art compiler for the JVM. In Graal, a compilation unit is a Java method. And Graal uses a graph-based IR in static single assignment form. In Graal, nodes represent either expressions or statements, and directed edges define either the controller or data flow. I would like to describe now our technique. Our technique for accurate profiling consists of 4 steps, namely the event occurrence identification, the instrumentation phase insertion into the compilation pipeline, the marker insertion to the third insertion of the instrumentation code, And finally, the instrumentation code generation that takes place at the end of the compilation pipeline. I will now explain each of these steps in detail. To identify the event occurrences of interest, we define a predicate for each event type. The predicate checks whether a certain AR node represents an occurrence of that event type. We would like to note that certain event types can be directly mapped to basic AR nodes, such as object allocations, while others must be identified with static analysis. Let's consider, for example, this expression, optional of character value of x. The AR corresponding to this expression is reported on the right-hand side of this slide. White nodes connected with solid arrows define the control flow, while purple nodes connected with dashed arrows define the data flow. We are interested in profiling two different event types, that are the if event type and the allocation event type. Hence, we iterate over the AR nodes and we test the predicates of these two event types, identifying one occurrence of the if event type and two occurrences of the allocation event type at nodes 2, 4, and 6. Each event type predicate is tested by a new compiler phase that we call instrumentation phase. If we have multiple event types, we have multiple instrumentation phases. The problem is determining the place in the compilation pipeline where each instrumentation phase should be added. Indeed, inserting the instrumentation phase at an arbitrary place in the compilation pipeline may lead to two issues. First, if the instrumentation is performed too early, the profiler could wrongly instrument, or miss, event occurrences that are removed or added by subsequent optimization phases. Second, if the instrumentation is performed too late instead, occurrences may not be identified because the compiler has lowered the corresponding AR nodes. Hence, event occurrences must be detected and then instrumented after that they've been fully optimized, but before they are transformed into low-level representations, and hence are not available anymore. For this reason, we insert our instrumentation phases, so the instrumentation phase of each event type, after the last phase where that event type can be identified. Each instrumentation phase identifies the event occurrences of a certain event type. However, does not insert any instrumentation code in the AR. Doing so will reduce the accuracy of the collected metrics. This is because instrumentation perturbs compiler optimizations. For example, instrumentation code may contain side effects that alter subsequent optimizations, control flow, and instruction scheduling. Moreover, instrumentation code may, for example, increase the size of the AR, reducing the code size budget of subsequent optimization phases. There may be, for example, method inlining. So instead of inserting the actual instrumentation code in the AR, we insert placeholder nodes that we call markers. Markers are no OP nodes that denote the execution of a certain event type. Markers have no side effects and no data dependencies. Considering, for example, the previously shown AR, we simply insert markers either before the occurrence of the if event or after the occurrence of the allocation events. Finally, after the execution of all the compiler and instrumentation phases, we replace all the markers with instrumentation code. We define, for this reason, a single instrumentation code generation phase, ICG, which is injected at the end of the compilation pipeline. This phase may implement different code generation strategies. In our article, we present three implementations, namely direct event counting, which is a naive implementation that increments an event counter at every marker location, path decoding that exploits path profiling to perform bulk event counter updates at the end of program paths, and finally, path counting that counts the number of times that a path is executed and computes the actual event counts offline using a path decoding table. In this presentation, due to a matter of time, we focus on path counting. We report here the previously shown IR. This IR contains two program paths. Both start at node 1, the start node at the top, and end with the return node 7 at the bottom. The first path goes through the true branch of the if on the left side, while the other path goes through the false branch of the if on the right side here. But this path end at the same point. Hence, we add instrumentation code only in a single point of this IR. Our instrumentation code for path counting is composed of two different parts, namely the path tracking and the path count update. Path tracking determines the path that is executed, while path count update actually updates the counter associated to that path. I would like to present here the use cases of our technique. When developing new optimizations, compiler developers need to carefully analyze the effects of their changes on the compiled code to assess the benefits. The problem is that changing one phase may have unpredictable effects on all the other compiler phases. Manually analyzing the IRs is time-consuming. Even though it may be a solution, this process is time-consuming, since an IR typically contains thousands of nodes. For this reason, we employ our technique to analyze compiler optimization phases. In our article, we show an example where we understand the reason behind the performance improvement. Second, we can employ our technique to simplify debugging. In our article, we show a use case where we identify the root cause of an expected slowdown introduced by a compiler phase. In this presentation, I'll focus on the first use case, hence explaining the reasons behind the performance improvement. In particular, we analyze the optimistic aliasing analysis OWA phase. This phase speculatively inserts information into the IR about which object pointers are actually the same, meaning they are aliased. The OWA phase allows other optimizations to perform, to optimize the code. These optimizations may be, for example, read elimination, write elimination, GC write barrier elimination, or vectorization. However, it's a priori unclear which of these optimizations are improved and to which extent. We noticed that OWA leads to a 15% speed up of the Renaissance benchmark ALS. Hence, we run ALS with and without OWA, and we look at event counts that significantly differ between the two executions. In this table, you can find in the first column the all and only metrics that significantly differ between the two executions. In particular, you can find some bulk metrics that are related to vectorization, and some other metrics that are, for example, loop end, if, and arithmetics. In the second column, you can find event counts collected for benchmark ALS for the metrics reported in the first column. These event counts are collected while using all the compilation phases. In the third column, instead, you can find the event counts for the ALS benchmarks for certain metrics when using all the compiler phases except OWA. By looking at the metrics, we see that vectorization metrics, that is, the bulk metrics, are much higher when OWA is enabled. This suggests that OWA enables vectorization of more loops. This is confirmed by the loop end and if metrics. The loop end and if metrics both decrease when using OWA. We would also like to notice that arithmetic operations decrease instead, due to fewer loop index updates, memory address computations, and scalar computations. We would also like to notice that there is no significant difference in Java object array accesses that are indeed not reported in the table. This suggests that OWA does not significantly affect read-write elimination in this case. Before concluding, I would like to briefly present the evaluation of the overheads of our approach on the Renaissance and the Capo benchmark suites. In particular, due to a matter of time, we report only the geometric means across all the benchmarks of all the suites for the path counting strategy when profiling 43 event types simultaneously. In particular, we have an average execution time overhead of 1.18x, an average compilation time overhead factor of 1.48x, and an average code size overhead factor of 1.49x. We would like to notice how the compilation time overhead and the code size overhead are strictly correlated. In our article, you can find a more extensive evaluation. In particular, you can find a comparison of the three different implementations we have previously described, namely direct event counting, path decoding, and path counting. Moreover, you can find a detailed evaluation that uses several event types categories. That is, we evaluate several subgroups of event types profiled at the same time. To conclude, we propose a novel technique for AR event profiling. Our technique efficiently and accurately profiles bytecode level and compiler-generated event types, reducing perturbation on compiler optimizations. We propose two path profiling strategies to reduce instrumentation overhead. Moreover, we propose a modification to the standard path profiling algorithm that makes it applicable to modern JIT compilers. We implement our methodology in accounting profiler for the Graal compiler, and we use our approach to identify the reasons behind the performance improvement and the causes of unexpected performance slowdown introduced by compiler phase. We evaluate our approach using the Renaissance and the Capo benchmark suites. Our experimental results show significantly lower execution time overhead with respect to an AV implementation. Finally, as future work, we plan to extend our implementations to support the collection of program execution traces. I would like to thank you for your attention, and I would be glad to answer your questions.
Right. Any question? Please.
So, yeah. Thank you, Matteo. Just curious, the marker operations, is it possible for later compiler pass to move or remove the markers?
So the markers are like placed attached to the node they refer to. So if a later compiler phase moves the code they kind of attached to, the marker is moved as well. So in this way we count for example, if the marker is attached to an if, and the if is moved, for example, outside of a loop, the marker is moved as well. So we actually count the right execution count in this sense.
Thank you. And I assume if the code is duplicated, loop is unrolled, the marker
Yes.
would be copied as well.
Yeah.
Right. Thank you.
Any other question? A quick one from my side. So I remember the Capo has different types of applications, right? So is there any domain where this techniques works better, or are the improvements, let's say, cross-domain? I think the Capo contains a ray tracer, for example, or the core of Eclipse, and these are very different applications. So does it perform? Can you correlate the performance of this technique to the type of the application, or is it really a cross-domain thing?
I would like to double check the article, but as far as I remember, it's like cross-domain. I would like to check each of them individually, but yeah, it's kind of cross-domain. There is no particular like behavior, unless in like particular benchmark where we have like dynamic code generation. So we have code generation at runtime, and there we have like a different behavior for that reason. But for all the others, like the overhead is like in line. It's the same, kind of the same. It's like, depending on the type of the application. Yeah.
Thanks. If there is no other question, then we are really in between you and lunch. Thanks for joining this session, and thanks, Matteo, again.
Thank you.